Welcome back to the deep dive. Today, we are getting incredibly small
Very small.
and frankly incredibly specific. Because if you're listening to this, chances are you already know your way around a nanoscribe.
Yeah, you definitely know the drill.
You know the joy of two-photon lithography, TPP,
Yeah.
that specific hum of the laser.
Yeah.
And that feeling when you print a perfect static microstructure.
The best feeling.
Right, like a tiny cathedral or a lattice or a buckyball,
Mm,
and it just looks absolutely beautiful under the SEM.
it does. But you also know the frustration that comes immediately after that excitement.
Exactly, the frustration. Because usually that beautiful static structure it just sits there.
Yeah.
It's a statue. If you want to make it move, if you want actual actuation, you hit a brick wall.
A massive brick wall.
It's either incredibly slow, like watching paint dry, or it requires these dangerous voltages that just fry your sample.
Right.
Or, and this is my personal favorite, you have to hook up some clunky external pneumatic system.
Oh, the tubes.
The tubes. With tubes that are literally 1,000 times bigger than the robot itself, which completely defeats the purpose of working at the microscale in the first place.
It really is the classic TPP dilemma. I mean, we can print geometry with practically infinite precision right down to the diffraction limit, but printing life or movement has been the bottleneck.
Definitely.
But that is exactly why we are looking at this new paper today. It's from Nature, published just last month, January 2026. Titled 3D-printed, low-voltage-driven ciliary hydrogel microactuators, led by Zimin Liu and colleagues.
And for everyone listening who actually runs these machines, and I know a lot of you do, we're going to get into the specific slicing and hatching parameters you need to replicate this.
Yep, we have a number.
Because they didn't use some custom $1 million built-in-a-basement experimental setup. They used a commercial system.
Which is huge.
But the headline here is wild. They have printed hydrogel micromuscles that respond in milliseconds, run on just 1.5 volts, and can survive hundreds of thousands of cycles.
It really is a significant leap. We're moving from static sculpture to active robotics.
Yeah.
And the mission for this deep dive is to look past just the printing specs, though we will cover them.
Of course.
But we want to focus heavily on the applications, because once you can print a microscopic hair that beats like a real biological cilium.
You can do some truly sci-fi things.
Exactly. We're talking about artificial starfish larvae, programmable fluid vortices, micro conveyor belts.
Artificial starfish larvae. I cannot wait to unpack that.
Hmm.
But before we get to the robot starfish, we have to talk about the secret sauce of the fabrication.
Right. The how.
Because our listener knows that standard hydrogels are usually sluggish. They're sponges. You apply a voltage, you go get a coffee, you come back, and maybe it's bent a couple of degrees.
Maybe.
How did this team get millisecond response times?
Well, it all comes down to the porosity, and this is where that TPP expertise really matters. Usually, when you're printing hydrogels or using molding techniques, you end up with a relatively dense block. Or if you do get pores, they're accidental, or they're in the range of, say, 10 to 30 micrometers.
Which is huge in this context. I mean, relative to an ion, a 30 micrometer pore is a cavern.
It's massive. But the walls between those pores are thick, meaning the diffusion path is really long. So Liu and his team used a commercial system, the Nanoscribe GT, and they tuned the parameters very aggressively.
Okay.
They set the slicing distance to 300 nanometers and the hatching distance to 200 nanometers.
Okay, so just to recap for the broader application here, or for those of us who usually just hit auto slice in the software, what does that actually do to the material physically?
So slicing is the vertical distance between layers, and hatching is the horizontal distance between the laser lines that are filling the shape.
Right.
By setting them to 300 and 200 nanometers respectively, they are effectively drawing the lines further apart than the voxel width would typically dictate for a solid fused structure.
So they aren't trying to fuse a solid block. They're intentionally leaving gaps.
Exactly. They created a network with nanometer scale porosity. We're talking pores ranging from 20 to 80 nanometers.
So they basically printed a nanosponge.
Precisely, a nanosponge, and this is the key physics insight. By creating that nanoporosity, they drastically increased the effective surface area of the electric double layer, the EDL.
The EDL. Okay, let's unpack that because that's a term that gets thrown around a lot in microfluidics. Why does a massive surface area inside the gel make it move faster?
Because actuation in these ionic gels is all about ion transport. You need ions to move from one side of the gel to the other to cause the swelling or shrinking.
Right.
In a dense gel, that's a really slow commute. It's diffusion limited. But with this nanopores network, you have these super highways for ions. This massive surface area facilitates super fast electroosmotic flow.
So the ions aren't just kind of drifting through the gel, they're being actively driven along these surfaces.
Correct. The electric field drags the ions along the huge surface area of the pores, and the ions drag the water with them. And that is why they are seeing bending responses in the range of zero point 0.1 to zero point 0.7 seconds, milliseconds, rather than the tens of seconds or minutes we're used to seeing with millimeter-scale hydrogels.
That is the game changer right there.
Oh,
If it takes a minute to bend, it's a science experiment.
Yeah.
If it takes milliseconds, it's a motor.
Exactly, it's an engine. And the motor itself, the material, is an acrylic acid co-acrylamide hydrogel, ACO-AM.
Okay.
But the other constraints they broke are honestly just as important as the speed. You mentioned the voltage earlier in the intro.
Right, 1.5 volts, which for anyone who works with biointerfaces or live cells is a magic number.
It really is, because 1.5 volts is roughly the threshold for the electrolysis of water. If you go higher, say 2 or 3 volts, you start splitting water molecules.
You get bubbles.
You get hydrogen and oxygen gas, which, if you're building a microrobot, is catastrophic. It's literally like your engine exploding.
Or at the very least, those bubbles create a ton of turbulence that just ruins whatever delicate microfluidics you have going on.
Exactly. By staying at 1.5 volts, they get this fast actuation without destroying the sample or the cells they might be working around. There are no bubbles. It's silent, smooth motion.
That's incredible.
But here is where it gets really interesting and honestly a bit counterintuitive. The direction the cilium bends depends entirely on what liquid it is swimming in.
Yes, this was the part of the paper that made me do a double take. I had to read the diagram like 3 times.
It's tricky.
So you have this little printed hair, you turn on the voltage. If it's in pure water, it bends left. But if it's in salty water, it bends right.
Basically, yeah. And understanding why is crucial if you want to actually use these for applications.
Okay, walk me through it.
So in deionized water, pure water, the mechanism is driven by hydrogen ions, H+. The H+ ions migrate to the cathode side, which is the negative electrode.
Right.
When they get there, they change the local environment and cause the hydrogel network to shrink.
Okay, so it shrinks on the left side, which naturally makes it bend to the left. That follows.
But put that exact same robot in physiological saline, which is full of sodium ions,
Yeah.
Na+, and the physics completely flips.
Because the sodium ions are different.
Yeah, they're much larger, and importantly, they carry a hydration shell.
Ah, they bring their luggage with them.
A lot of luggage. So when the Na+ ions migrate to the cathode, they drag a huge amount of water molecules with them into the gel. This causes the hydrogel on that side to swell massively instead of shrink.
So it swells on the left, which means it bends to the right, towards the anode.
Exactly. It's a complete reversal driven just by the competitive ion effects. It's a brilliant demonstration that the environment is just as much a part of the robot as the printed material itself. You have a single actuator that behaves completely differently based on context.
That is wild. It's like a machine that runs in reverse depending on what kind of fuel you pour into it. Okay, so we have a fast, low-voltage, environment-sensitive actuator.
Yeah.
Now let's get to the mission of this deep dive. What can we actually do with it? Because the paper moves pretty quickly from look at this bending hair to some really incredible arrays.
This is where we transition from material science to actual robotics. Imagine a forest of these microcilia. Each one is roughly 10 micrometers in diameter and somewhere between 18 to 90 micrometers tall.
Tiny.
Very. And around every single hair, they have patterned 4 individual microelectrodes.
Wait, around every hair. So every single hair is individually addressable.
Yes. And that is a massive step up from, say, magnetic actuation.
Oh, for sure.
Usually with magnetic cilia, you apply an external magnetic field, and the whole forest moves together. It's a synchronized dance, but you can't tell one hair to move left and the other right.
Right, it's global control versus local control.
Exactly. Here, they built a 5x5 array where they could control every pillar independently. They essentially made a pixel display where the pixels were moving hydrogel pillars.
I saw that. They even spelled out HKUST and MPII, the acronyms of the research institutes.
Yeah, a bit of a flex.
It's like a card stunt at a football stadium, but microscopic.
That's a great analogy. But instead of just looking cool, these moving pillars manipulate fluid. And this is the first major application, microfluidic mixing and pumping.
Okay.
By arranging the cilia in specific patterns, say spinning the outer ring clockwise and the inner ring counterclockwise, they created very specific vortex arrays.
And we aren't talking about a gentle drift here. They clocked flow velocities between 50 and 250 micrometers per second.
Which at this scale is extremely significant. In microfluidics, mixing is notoriously difficult because the flow is laminar, it's smooth.
Right, the fluids just sort of slide past each other like a layered cake.
Exactly, they don't want to mix. To get them to mix, you need turbulence or vortices. And these programmable arrays can generate those vortices on demand.
So you can actively pump fluid through a chip or mix two reagents together without needing any external pumps or tubes hooked up to the system. The pumps are literally printed directly inside the channel.
Yes. It simplifies the whole lab-on-a-chip architecture immensely.
Okay, that brings us to the application that I know you were excited about.
Uh-huh.
The biomimetics, the artificial starfish.
Oh, this is, in my opinion, the most profound part of the study. You see, in nature, microscopic organisms don't use propellers, they use cilia.
Right.
Starfish larvae, for example, have this beautiful, intricate band of cilia all around their bodies, and they beat these cilia to create vortices that pull food towards their mouth and help them swim.
And capturing that complex motion has been really hard for engineers to replicate,
It's
right?
extremely hard. I mean, we've had theoretical models and we've had kind of clumsy macro-scale robots, but this team actually printed the complex curved body shape of a starfish larva, a sort of bipinaria shape.
Okay.
And then they printed the active hydrogel cilia directly onto that curved surface.
And that's the key right there, isn't it? Printing on a curve. Because TPP is usually done on flat glass slides.
Correct. They integrated the electrodes and the gel on a 3D, non-planar surface. And when they turned it on, the artificial larva generated the exact same vortex arrays that a real biological starfish larva creates.
So they didn't just make it look like a starfish, they actually manipulated physics exactly like a starfish.
Precisely. And so what here is huge for biology? It creates a platform for quantitative study.
How so?
Well, biologists have always struggled to measure active boundary conditions, basically exactly how the fluid interacts with a swimming organism. It's really hard to tell a real starfish larva to swim at 50% power so you can measure the drag.
Yeah, the starfish is a terrible employee.
Terrible, uncooperative, but the robot does exactly what you tell it. Now, instead of trying to measure a squirming, unpredictable larva under a microscope, you can build a robot version, control every parameter perfectly, and measure the fluid dynamics precisely.
It bridges the gap between engineering and biological discovery. It's basically a wind tunnel for microorganisms.
That is a fantastic way to put it. Yes, a microscopic wind tunnel.
But they didn't just stop at biological copies.
Yeah.
They also started building machines, like real mechanical linkages.
Right. And this addresses another big criticism of soft robotics, that it's too squishy to do real work. People always say, sure, it wiggles, but can it push a lever?
Can it actually affect the rigid world around it?
Exactly. So they demonstrated a flapping micromachine. They printed a rigid arm, a mechanical linkage, and connected it directly to the soft hydrogel actuator.
So the gel bends, and it pushes the rigid arm.
Yes. It successfully converts that soft swelling motion into rigid kinematic motion. It's like a microscopic piston engine.
Wow.
This opens the door to complex micromachines that can grab things, lift things, or lock components in place.
And we touched on this a bit with the starfish, but I really want to emphasize the substrate versatility here. Because our listeners might be thinking, okay, cool, but I can only print this on a highly conductive, perfectly flat glass slide.
Not anymore. They fabricated these arrays on flexible polyamide films.
Yikes.
They wrapped them over hill-shaped surfaces with a 100 micrometer height difference. They even printed them on pyramids and helical shapes.
Which means you could potentially wrap these actuators around a catheter or an implant.
Exactly. You are no longer limited to flat, rigid ships. You can put active, beating cilia on surfaces that heavily resemble complex biological tissues.
Okay, I have to play the skeptic for a second, though.
Yeah.
Because this all sounds amazing. Starfish, pumps, flapping levers.
Yeah.
But usually when we talk about ionic actuators in TTP, there is a catch.
There's always a catch.
And the catch is usually that they burn out after a few hours.
Mm.
Did they address the durability of these things?
They did. And the numbers are actually surprising. They ran these actuators for 330,000 continuous cycles.
Wow.
That is 5 straight hours of continuous beating at 20 hertz.
And did it just fall apart?
They saw less than 30% performance degradation.
That's it.
For a soft ionic material, that is incredibly robust.
Why didn't it degrade more? Because usually electrodes corrode or the gel just physically falls apart.
It goes right back to the voltage. Because they are operating at a mere 1.5 volts, There is no electrochemical reaction happening. There is no redox. No chemical bonds are being broken and reformed constantly.
Oh.
It is purely physical ion migration. The ions move in, the ions move out. The material itself isn't being chemically consumed.
That is a huge distinction. It's a physical battery, not a chemical reactor.
Right.
But there is a right, I remember reading something about a complex fluids limitation in the discussion section.
Yeah, there is a limitation. The system works beautifully in deionized water. It actually works surprisingly well in human saliva, too.
Saliva, really?
Yes. Saliva is mostly water and simple electrolytes, so it's consistent enough. However, when they tested it in actual blood serum or plasma, the performance dropped significantly.
Why is that? Is it the viscosity of the blood?
Partially, but it's mostly the ion soup problem.
The ion soup.
Yeah, biology is messy. Blood serum is full of magnesium, potassium, calcium, various proteins. It's just packed with huge molecules and tiny ions all fighting for space.
It's that crowded dance floor again.
Exactly. You have competitive ion effects. The sodium wants to swell the gel, but maybe the potassium interferes, or the magnesium binds to the sites. The swelling efficiency drops simply because there are too many different ions fighting for the exact same parking spots in those nanopores.
So if I want to put this in a bloodstream to scrub arteries or something, we aren't quite there yet.
Not with this specific chemical formulation, but the expert analysis in the paper suggests that to solve this, we just need to optimize the chemistry.
Okay.
Perhaps adding different monomers like AMPS to handle the ionic complexity better, or ironically making the cilia even smaller.
Smaller, how would that help?
If you reduce the diameter to, say, 2 micrometers or less, you reduce the absolute distance the ions have to travel to actuate the gel, which might be enough to help overcome that traffic jam in complex fluids.
So the solution to the problem of being too small is to get even small. Typical nanotechnology.
Always.
Okay, let's zoom out a bit and recap what this means for you, the listener. We started with a brand new way to use your TPP machine.
Right. By tuning your slicing to 300 nanometers and hatching to 200 nanometers, you can turn a standard commercial resin print into a high-speed ion sponge.
We have a mechanism that is incredibly fast, milliseconds, and low voltage, 1.5 volts.
And it's completely reversible based purely on the salinity of the fluid it's in.
And we have applications that are actually useful out in the real world. Fluid mixing, programmable vortex arrays, and biomimetic robots that can mimic nature's most efficient swimmers, even on curved surfaces.
And it's durable enough to run for hundreds of thousands of cycles without falling apart.
It really feels like a pivotal moment. We so often see TPP used for static metamaterials, lenses, trusses, things that just sit still. This feels like the moment TPP truly becomes a robotics tool.
I think that's the correct takeaway. We are finally bridging the gap between static print and living robot. The ability to print active movement with this level of resolution fundamentally changes the design constraints. You don't have to design around a separate motor anymore. The material is the motor.
So here's my final thought for you, the listener, to mull over. We've talked about mixing fluids and robot starfish. But if we can now print active cilia on curved, flexible substrates, and they can survive hundreds of thousands of cycles, are we looking at the precursor to active artificial skins?
That is a fascinating thought.
Right? Just imagine a medical implant coated in this active skin. It doesn't just sit there in the body. It uses these microscopic cilia to self-clean and constantly sweeping away bacteria before a biofilm can even form.
Oh, wow.
Or it actively transports fluids across its surface to deliver drugs to one highly specific spot on an organ.
Active boundary conditions inside the human body, that would be completely revolutionary.
The bridge between a static print and a living robot just got a whole lot shorter.
It really did. And for those of you itching to try this on your nanoscribe today, check the show notes. We have listed out the specific slicing, hatching, and developing parameters from the Liu et al. Paper, so you can try replicating that nanoporosity yourself.
Go forth and print some muscles. Thanks for listening to The Deep Dive.
See you next time.